This video, we're going to talk about series and their notations. I'm going to use the calculator quite a bit today to show you that some of this can be done on your TI-84. So our series are going to be something that we're going to see in both statistics as well as in calculus. So let's go ahead and let's talk right now about where we're going to see this. So in statistics, we're going to have something like leaving myself some space there. Sometimes your formula will have a little index like I that goes from 1 to n. That's just going to mean whether you see the index there or the counters there or not, that it's going to go from your first term in your list plus your second term in your list plus all the way out to your last term in your list divided by the number of things in your list. You've been doing that for a while. If you've been finding your average for your tests or your average for your homework or anything like that that you have, especially if you have weighted grades in your class, you would have been doing this to help find your grade in the class. Another place that you're going to see them if you are in calculus, like I was saying before, is that we're going to see series that are related to summations. So we get this formula that the definite integral is equal to and I'm not going to talk about what all that means right there, but you see that there is a summation right here in that definition. So you're going to need to know how to do that. This is in Calculus 1 in like chapter 4, usually. That's in our textbook where we use the Larson textbook. I've done some stuff with Apex Calculus as well in my videos. It's around the same place in there. Chapter numbers are a little different in the Apex Calculus textbook. So in Calculus 2, there will be a whole section on infinite series, which this is an infinite series right here, but you'll learn a whole lot of rules for convergence and divergence of infinite series, and you need to understand how to read them and how to figure out if a series is finite, has a finite number of terms, or infinite. And we're only going to be talking right now today about finite series in the beginning, but we might get to the general formula for an infinite geometric series, which is something that's at the very end of Calculus 2, but we can talk about it right now in pre-calculus. It's just something that you can look at and you can come up with the answer. So if we get any examples of that today, we'll talk about that. All right. Let's talk about definitions and notations first, and then we're going to use the summation notation to write a sum, and then we're going to find the sum of the first n terms of an arithmetic sequence using our series. So we can talk about sums of geometric series and things like that as well. That's in the textbook, but today on this worksheet, we're only going to talk about summations of arithmetic sequences and series. So inside the series goes the explicit formula for the kth term or nth term or ith term, whatever this counter is here of the series. This is going to be a sequence, a formula that generates the sequence of terms. And this is going to be the index for the subscript of the first term that you're interested in adding to the last term of the sequence that you're interested in adding. You don't always have to start at the first term, but it helps us with our formula if we do. So let's go ahead now and let's just look at some examples. For example, the series 1, 6, 11, 16, 21, 26, and 31 has a general formula in the form of an arithmetic sequence of 5n minus 4. If we stick in n equals 1, we get 5 times 1 is 5, minus 4 is 1. That generates our first term. We're taking steps of 5 every time. 1 plus 5 is 6, plus 5 is 11, plus 5 is 16, plus 5 is 21, plus 5 is 26, plus 5 is 31. There's 1, 2, 3, 4, 5, 6, 7 terms there that we're interested in. So we're going to write it the summation of, and we're going to put parentheses around this. Let's try and make that a little cleaner. Still not writing it very well. One more second here. Try this one more time. It's about as good as I'm going to get it today, unless I zoom in a little more. They didn't leave very much space there. Okay, there we go, 5n minus 4. And the reason we want parentheses is we want to be clear that n gets plugged into that whole thing and that we're not doing the summation of everything and then subtracting 4. We want to be very clear that we're adding this 5 times 1 minus 4 plus 5 times 2 minus 4, 5 times 3 minus 4. We don't want to be ambiguous at all, so parentheses are going to help us out. This worksheet's not going to use parentheses a whole lot. I'm going to try and add them like I just did there to clarify things like that. We're going to need to recognize special patterns, like we're going to see the denominators here increasing by 1. So the denominator here was 1, 1, then 2, then 3, then 4, then 5, and the numerator stayed as 1. So this is 1 over n. This is a special series in calculus called the harmonic series. It has to do with the motion of a spring. Don't worry about that unless you're going to be in physics and you're going to study harmonic motion like that with Hooke's law. But it is going to be 1 plus a half plus a third plus a fourth plus a fifth, something like that. The first 5 terms of that are listed there. If we want to add them together, we change these commas to plus signs, and we add them together and we get an answer. Similarly, this denominator is 1, but this is all perfect squares in the denominators. 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. So we need to recognize our perfect squares. So we've got n equals 1 to 6 of 1 over n squared. This last one is going to be powers of 3. So it's 1 over 3 to the first, plus 1 over 3 to the second, plus 1 over 3 to the third, plus 1 over 3 to the fourth, plus 1 over 3 to the fifth. So we're going to write that as 1 over 3 to the n equals 1 to n equals 5. We could also write that as n equals 1 to 5 of 3 to the negative n because of rules of exponents. Or we could write it as n equals 1 to 5 of 1/3 raised to the n because 1 to the n is always 1. So this is going to be probably the most useful way for us to write it in calculus. But you're going to see it written some of the other ways there. Okay, so now we're going to talk about specifically how to quickly add up all of the terms of an arithmetic sequence where they have a common difference. This only works for arithmetic sequences, doesn't work for geometric or anything that's not arithmetic or geometric. So where the first term is A1 and the nth term is AN, we're going to add those two together and we're going to multiply times n over by n over 2. I'm going to take an odd number, no, an even number of terms so that they can be paired off evenly here, and you're going to see how this works. Let's just take 1, 2, 3, and 4. The first 4 counting numbers. 1 plus 4 is 5. 2 plus 3 is also 5. So if I add them up and get 5, I'm going to multiply because I'm going to have 2 groups of 5 because 4 divided by 2 was 2, and this would add up to be 10. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. 10 is my answer. But it was faster for me to figure out 5 times 2 was 10 than to go 1 plus 2 plus 3 plus 4. It gets much harder when you get larger numbers of terms, and that's why we're going to use that multiplication technique instead of the addition technique when we get like 30 terms and 50 terms and so on, like we have in these examples. Then we're going to do one ourselves for the first 30 terms of this by hand. But these first two, maybe all 3 of these get worked out for us. I think all 3 do. So let's look at this example. Sum of the first 30 terms of the arithmetic sequence, it starts at 7 and has a common difference of 3. So if we want to go 30 terms out here, we know our A1, we know our D, we know our N, but we need to find our A30. So we're going to plug that into our formula that they have right here, that AN is equal to A1 plus N minus 1D. That's going to give us 7 plus 29 times 3. In our calculator, we're going to see that 29 times 3 is going to give us 87, and then 87 plus 7 is going to give us this 94. So our 30th term is going to be 94. We go ahead and we say our A1 was 7, our A30 was 94, and our N was 30. So we should be able to plug it into this SN formula now. The S30, which means the 30th partial sum. We haven't talked about what partial sums are, but the sum of the first 30 terms, 30 divided by 2 times 7 plus 94. 30 divided by 2 is 15. 94 plus 7, 101. 101 times 15 is 1515. Let's do part B. The sum of the first 50 terms of the arithmetic sequence whose general term is AN equals 2n minus 5. We need to find A1 and A50 and then substitute into the formula. So A1 is going to be 2 times 1 is 2, minus 5 is negative 3. A50 is going to be 2 times 50 is 100. 100 minus 5 is 95. Now that we have negative 3 and 95 and 50, we can go ahead and substitute into our formula here. 50 divided by 2 is going to be 25. 95 minus 3 is going to be 92. 25 times 92 is going to give us 2,300. And that was way better than adding negative 3 plus, what was our common difference here? 2 plus negative 1 plus 1 plus 3 plus 5, all the way out to 95. That would have been a lot of adding to do to get 2,300. Let's look at this third example here. Now I've got a couple ways I can do this. I'm going to do this a way that we're going to do it with calculus, as well as the way that we're going to do it here with pre-calculus. And I'm going to show you that it's the same thing. So I equals 1 to 30, 6i minus 4. So let's follow this pre-calculus way first. We're going to stick in 1 for the first term, and we're going to get 6 minus 4, and that's going to be 2. So our first term is 2. Our 30th term is going to be 180 minus 4 is 176. 2 plus 176 is going to be 178. Not 30 terms. 30 divided by 2 is 15. 15 times 178 is going to give us 2,700 or 2,670. Now let's do this with some shortcut formulas that we know from Calculus 2. I'm just going to introduce them now. I equals 1 to n of a constant is going to be c times n. That's just the definition of multiplication. I equals 1 to n. This is a special version of the formula that we're talking about right now. N times n plus 1 over 2, where the initial term is 1 and the last term is n. We add them together and multiply by n over 2. It's the same formula. It's 1 to n of I squared equals 1 to n of I cubed. The I cubed formula is just the perfect square of this formula. And this one is n times n plus 1 times 2n plus 1 divided by 6. So I'm going to take a slightly different tact on this one and say that if I say I equals 1 to 30 of 6i minus 4, that's going to be 6 times I equals 1 to 30 of I minus I equals 1 to 30 of 4. So this is 6 times 30 times 31 over 2 minus 4 times 30. This is going to be 3. So this is going to be 3 times 30 times 31 minus 120. And we get the same answer. So it doesn't matter whether you use this pre-calculus method or whether you use the calculus 1 and calculus 2 method with the shortcut formulas. It's going to work out the same way. You're going to get your summation to be 2670. All right, let's find the sum of the first 30 terms of the arithmetic sequence. That is 16, 10, 4, -2, -8. So my D here is -6. It's arithmetic. My A1 is going to be 16. I need to find A30. To do that, I'm going to have to say that A30 is going to be equal to common difference of -6 times n minus 1 plus my 16. So -6 times 29 plus 16. It's going to give me -158. Then my S30, this is all part A, is going to have to be 30 over 2 times 16 minus 158. So 15 times 16 minus 158 is negative 2,130. Let's check that a different way in our calculator. Math, summation, x equals 1 to 30. And our general formula here looks like it is negative 6x plus 10. Okay, I'm going to trust the formula they gave us here. So this is my A1. My AN, again, should be A30. Is going to be D times N minus 1. So 30 minus 1 is going to be 29 plus my A1. So that's going to be negative 6 times 29 plus my 16. And that's my negative 158. Add that to my 16. It's going to be negative 142 times my 15 is going to give me my negative 2130. So now let's find the sum of the first 50 terms whose general form is this. So this is easy enough to just stick into the calculator. But let's do it with A1. This is for part B. A1 is 2 plus 1 is 9. A50 is 107. When I add those together, I get 116 times 50. I get 5,800. It's from 1 to 50 of 2x plus 7. I did get half of what I got. Oh, I forgot to divide this by 2. 50 over 2. Thank you, calculator, for checking me. Okay. Then I've got that was 3. This was 2. Number 4. Find the sum of, so we've got A1 is equal to 7 minus 5 is 2. A30 is 210 minus 5 is 205. Got 30 terms, so 15 times add 205 and 2 is 207. is 3105. All right, so I think that that's it. Yep, that's it for this worksheet. Lots of other applications to this with series. Like they mentioned up top, we can use this for annuities, as well as finding the sum of an infinite geometric series, which is important in calculus. If we want to write a function f of x that gives the summation of that. Let me just give you a couple formulas here from what they're talking about. So if I have in this form n equals 0 to infinity, a0 r to the n, if and only if r is, the absolute value of r is less than 1, then this is going to be exactly equal to a0 divided by 1 minus r. So for the example that I had earlier, that was 1 times a half is like this, plus a fourth, plus an eighth, plus a 16th, and so on, and it's an infinite series, right? Then that's exactly equal to 1 over 1 minus a half, which is 1 divided by a half, which is exactly equal to 2. So that's one of the things that they would go over in the textbook here. Another thing that they might go over in the textbook, they might not, because this is more a calculus 2 thing, is that we can take anything that's in the form of 1 over 1 minus x, and f of x that's written in the form of 1 over 1 minus x, or like this, we can go the other way and say if f of x is equal to, say, 5 over 1 minus x, like that, well, then we can write that as the infinite series of n equals 0 to infinity. This a0 is 5. Our r is going to be x, and it's going to get raised to the n, like that. If this was f of x is equal to 5 over 1 minus 2x, then this would be n equals 0 to infinity 5 times 2x raised to the n. And you have to put parentheses around the 2x. So I can take a function and write it as an infinite series. I can go from an infinite series and write it as a function like this. And that's something that we do in calculus 2 a whole lot. It's pretty neat. So I think that that's what they were talking about here when they were talking about using the formula for the sum of an infinite geometric series. And to find the sum of the first n terms of a geometric series, it's a little bit of a variation on this one, but it's pretty close to that. So, all right, we are going to come back and talk about some other counting principles next time, and those are going to tell us about some other patterns we talked about, knowing your perfect squares and perfect cubes and powers of 3 and things like that. So this we're gonna need to take one step in between before we go when we look at something called Pascal's triangle that has lots of patterns in it. And we need to talk about another topic called combinatorics. It's super important for both discrete math and statistics. So those general counting principles, as well as specifically combinations, is what we're going to talk about next time in our 9.5 video. See you next time.